Let's start today's physics lab for electricity, magnetism, and light. This is Unit 1. In today's lab, we'll look into static electricity concepts, which includes origin of charges and attraction and repulsion of charges. Then we'll explore how these interactions leads to other physical phenomena such as electric force, electric fields, and electric potentials. We'll also demonstrate what variables affect how charged bodies interact with each other, describe the strength and direction of the electric field around the charged body, and calculate the electric potential due to a single charge or multiple charges. Electric charge. Electric charge, it originates in atoms. Uh, um, Atoms are the building blocks of any materials. Atoms consist of three main particles, also called the subatomic particles. Uh, there are protons and neutrons at the center in the nucleus. The neutrons are chargeless particles that help to glue the protons together, or call it they are bound by this strong force. And the other particle electrons form these orbit-like structure, but they're actually in the form of clouds around it, surrounding the nucleus. And the electric charge is the property of these subatomic particles like proton and electrons. uh, uh, you know Here example is shown for the carbon atom. It has six protons glued together by six neutrons inside the nucleus, and there are six electrons orbiting around the nucleus. So these subatomic particles here, have two main properties. One, they have mass and they have charge. It just the neutrons do not have charge. I'm only talking about the protons and the electrons. And the charges have two flavors, and this is the, I should say, the natural property. The term positive and negative are arbitrary, meaning the electron and protons, what we know is they have two different flavors. It's just that for one flavor we started calling positive and the other the negative, and so we started calling protons to have a positive charge, electrons to have a negative charge, and we stick to that. Okay. Electric charge is conserved. Let's look at the unit of the charge. So each of the charge here have magnitude um, value, the numerical value of the charge. Similar, like it has mass, right? The mass of the electron about 10 power minus 31 kilograms. So that's the magnitude of its mass. Similarly, the magnitude of the charge of the electron is it's negative. So for electron, we'll use as the negative sign here. Its magnitude is 1.602 times 10 power minus 19 coulomb. So the unit of the charge is coulomb, and if it's a positive charge, it's remove the negative sign, and that's just positive 1.602 times 10 power minus 19 coulomb. And the again, so these charges have two flavors, positive and negative. If you rub a glass rod, on a piece of cloth, then it loses the electrons. The electrons are, you know, brushed off uh, to the rubbed material, and they get net positive charge. And if you have two of these glass rods with the same charges, and if you bring them closer together, one repels the other. That's the repulsive property. And while rubbing the ruler, a plastic ruler, on the same piece of cloth, this ruler gains the electron, it attracts electrons from the piece of cloth, and hence it attains net negative charge. And if you bring the glass rod to it, now these are two different flavors of charges. These charges attract each other, and the ruler, rotates in this fashion or clockwise if you see it from the top. And the conservation of charge means, the charge were not created, simply by rubbing the ruler in the cloth. It gained, or it attracted the electrons from the piece of cloth, and there is excess of electrons here, and that means it would leave the piece of cloth with net positive charge, because the atoms in the cloth left the electrons. So if you look at it here, and every atom is electrically neutral, right? Meaning it should have equal number of proton and equal number of electrons. And these are atomic number. For all elements, they have their own numbers based on the number of protons and electrons. Carbon atom, this one is electrically neutral because there are 6 protons neutralizing the 6 electron. But if you had to remove 1 electron from the carbon, it would have net positive charge, and we call that the positive ion, because 1 electron left, so there is now one more proton than the electron, and you're going to add electron here, and so that means there would be it would have more negative charges, hence it would be a negative. Two things are happening here: the repulsion and the attraction, right? So this glass rod here is exerting force on the one that is hanging, right? So there is a force of repulsion here, and there is a force of force of attraction here. Last semester we did two types of forces: the Newtonian forces that were, uh, you know, the contact forces, F equals to ma, and we did the non-contact forces like the universal gravitational, Newton's law of universal gravitation, the attractive force between any two bodies in the universe. That was the non-contact forces. When one exerts force on the other without touching, right? And so that means here, what is that value, right? In physics, we generally quantize things or get the magnitude of the force. We know there is a force here, right? Here the repulsive force, there's the attractive force. What is that force? So to get the magnitude value, which is the Coulomb's law. Coulomb's law says that the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance, and we write it as F equals to some constant, proportionality constant K. So the magnitude of the force between two charges, as I was explaining, is proportional to the product of the two charges, um, and inversely proportional to the square of the distance between them. This is very similar, at least to uh, the Newton's gravitational law, universal gravitational law. Force is equal to constant, gravitational constant g, product of the mass is divided by the distance square. They both are called the inverse square laws. Um, these are both forces. The force that one charge exerts on the other, that this force could be repulsive or attractive. Um, uh, has units of Newton. The gravitational force, however, is always an attractive force, and the unit is still newtons. Here, masses play the role. Here, the charge. Okay. The constant value K and G are given as follows. So, if the same charges uh, are placed in space here, separated by distance r, this you'll do in class as the subscript. You follow this subscript, it's helpful. um, Here this means force on 1 due to 2. This is a repulsive force. So Q2 repulses Q1 to the left, and Q1 has repulsive force on Q2 to the right. So this is F21, this F12. The direction is equal and opposite. And if they are opposite charge, so there is an attractive force. Here uh, this arrow is a vector because force is a vector. You'll do, I'm sure, plenty of examples in class. Uh, Adding forces together, subtracting forces together. When I say adding forces and subtracting, you're doing vectorial addition and vectorial subtraction. I hope you haven't forgotten vector from last semester. And there is next the electric field. Or before going to that, the concept of these uh, non-contact forces, right? Here, one charge is attracting the other, or there is a repulsive force that's happening here. So, and that's happening without touching. That's the key to understand. How can one charge, repulse or attract, pull the other charge without any contact? Okay. For this, we have to understand electric field. So it happens that for every charge, either positive or negative, it has this electric field lines around it, and that originates from the charge itself, and it propagates outward or inward to infinity. So for a positive charge, and these field lines have directions, and for positive charge we consider the field lines to start from the origin, from the center, and emanate outward. How far does this field line go? To infinity, okay, for a single charge. And same thing, there is an electric field surrounding a negative charge, and that for negative charge, the electric field line, we consider it to be directed inward towards the charge. So these, once you place these charges in space, at instant, or if let's say it's just a circle here drawing, it has no charge. As soon as I put some negative charge in it, or positive charge, it instantaneously develops its electric field line emanating outward. I say instantaneously, in reality, these electric field lines move out at the speed of light. And so that means when I have a positive charge here, it almost instantly sets off this electric field line around it. And now when I bring a negative charge closer or at that distance here, meaning now there is this electric field line interacting with each other. Hence, these two charges have attractive force because of that, interaction between the electric field. Okay. And mathematically, the definition of the electric field is force per unit charge, right? The That gives the magnitude of the electric field. How much, what's the strength of the electric field around this positive charge? To know that, I can simply put a test charge with any other test charge, okay, and that test charge I'm picking it to be positive. So this q small test charge q here, if I place it here, a positive charge, this is another positive charge. So now there will be a repulsive force between this, right? So that means this bigger charge here will exert force on my test charge. And by measuring, how much force is exerted on that charge, gives me the electric field. And that's what the definition of the electric field is. And so the unit of the field from here is Newton. Force is measured in Newton. Charge is measured in Coulomb. Hence, electric field is measured in Newton per Coulomb. We can also derive a different formula, without the electric field, just the without the electric force, just the electric field due to a point charge. And here I can use the same test charge somewhere here, and by definition electric field is force divided by charge, force per unit charge, and that force is the Coulomb force between two charges, and that Coulomb force is kq times q being the bigger charge and small q being the test charge, divided by the distance square, distance between these two charges, and q cancels, the test charge cancels, hence the electric field due to any point charge is equal to kq divided by r square. This also follows the inverse square law, 1 over r square. What that means is, as I go away from the positive charge here, the electric field should decrease, right? Closer to the charge, stronger field. As I go further out, smaller or reduced electric field. And how much does the electric field gets reduced is that given by that 1 over r square rule here. It goes down by 1 over r squared, or 1 over distance squared. And so these are electric field drawings. To complete it, if I get two dipoles, same magnitude charges, but different charge. Um, Same magnitude meaning the magnitude of this charge. If it's electron proton, remember electron and proton have same magnitude, 1.6 times 10 power minus 19 coulomb. It just the sign is different. Then they would have electric field in this pattern here. If you bring two positive charges together, they repel each other, right? And as you can see here in the field diagram, so all these fields are diverging away, and it's it's almost impossible to do this in lab or practically showing this, but you can bring two magnets together because magnets poles behave similarly. If you bring two same poles of a magnet together, you feel that force when you try to connect the same poles together, because their field looks very similar to this one here. And Here, if you have a straight line like this, just a single charge, that straight line demonstrates the direction of the electric field. In curved field line like this, you know, at that instant here where P is, where is the electric field directed? You just have to draw a tangent line to this circle here. Tangent line is a line that grazes through a curved surface. So electric field here is directed along this vector here, and at that point there, the electric field would be horizontal to the bottom line. Okay, one more thing here. So I'm sure you've learned this in the theory class. The density of the line here represents the mm, the magnitude of the charge itself. Meaning, there are two things here. So you see these lines here, it gets more dense, or this area become smaller as as this line move closer towards the charge, meaning the strength of the electric field is stronger here. And as you see, as you go farther out, away there, here, and if you take a point P here, this point P is much farther out from any of these two lines, right? So that means the electric field is weaker here compared to there. Also, these lines can be proportional to the magnitude of the charge. So here, this is one positive charge, and it's shown 1, 2, 3, 4, 5, 6, 7, 8. So 8 field lines, right, is equivalent to one positive charge. If I were to put two positive charges here, then I would need 16 lines around it. So these field lines are proportional to the magnitude of the charge. And I'm giving example of positive charge only, same thing for the negative charge. And the last concept is the electric potential. So we did electric charge, electric force, electric field, and now the electric potential. Electric potential is potential energy per unit charge. Uh, the electric potential energy, the concept, it's very similar to gravitational potential energy. The gravitational potential energy is by virtue of height. When you raise some object at some height h, that object possesses some gravitational potential energy that is equal to mgh, mass times gravity times the height. Here, we take these two plates as example, two metal plates. We have put some positive charges in here with net charge plus q, and here the net charge negative q. And we know that the electric field lines originate at the plus charge and ends in the negative charge. So you'll have this homogeneous electric field going from the positive plate to the negative plate. So this one works like a potential for any charge. So this red dot here is any charge that has charge smaller q. Okay, for this q, it's like a rock raised from the ground higher up. Okay, and now that rock is in the gravitational potential, and the energy of that rock is called the gravitational potential energy. Similarly, by separating plates like this, there is an electric potential between the plate, that electric potential, and now placing a charge here in the positive side, this rock has this charge has electric potential energy, and potential energy is represented by U. And we say the V, or the electric potential, is the, again, here are two terms I may have mixed up. Electric potential energy is U, and just electric potential by itself, or just potential, is V. Okay, so V is electric potential energy per unit charge. I was explaining this charge being at the positive plate here is at, we call that at high potential. So when you raise a rock higher from the ground at the top, the rock has high potential, right? When you drop the rock, it goes to the bottom, and now the at the bottom the rock has low potential, and on the top the rock has high potential energy. Same way, this positive charge here at q, so all these positive charges here is going to repel the negative charge, and it will accelerate towards the negative plate. So here the positive charge has high potential energy, and when it gets to the negative plate, it rests there, it stops there, and it has low potential energy on the other end. Again, potential energy and potential are two different things. It's just that we need the help of potential energy to define electric potential, and that's what the definition is: potential energy per unit charge. Okay, and that's one definition. We can also define potential in terms of the electric field. If we know the strength of the electric field between the plates, that's capital E, and if we know the distance between these two plates, that's delta x, we can calculate electric potential, and that's capital V. V equals to E times delta x, or E times D, D being the difference, the distance between the two plates. The unit of electric potential is volts, uh, and I can rewrite this to solve for electric field. That will do for the lab today. That electric field is V delta V divided by delta X, or V2 minus V1 divided by X2 minus X1. The difference in voltage divided by difference in distance. For our lab purpose, we'll take examples like this. We'll put a positive charge here. So, if I have a positive charge line here, it has electric fields going out. How far do they go? To the infinity. Okay, it decreases, right? And where do they become zero? At infinity. And so that means at any point along the field line here, I should be able to find the electric potential. And that happens to be, I don't have the formula here, that's the potential due to a point charge is just kq divided by r, not a square, just kq divided by r. And potential is a scalar quantity compared to electric field and electric force, which are vector quantities. And so in the lab, we'll measure the potential due to a point charge at anywhere along this line. Okay, so and we'll measure the potential or the potential difference. Here I have labeled these four terms here, which in physics are basically the same thing. Okay, electric potential, or we just call potential most of the time. When we're studying electricity course, potential always means electric potential. If you are doing mechanics and you're studying gravity, the potential means gravitational potential. Okay, so here if you're reading book and you come with these terms, electric potential, potential, or potential difference, or even voltage, they all mean the same thing. And here I was going to explain about the potential difference, because even when measuring the gravitational potential energy, we always measure that difference between some height with respect to what? To the ground. So we always measure the difference, right, between any 2 points. Similarly here in physics, in theory or lab, we measure the potential difference between 2 points, okay, or between two different potentials. Here one potential, here the other potential. The positive ends are always called the high potentials. Here these ones are called the low potential. When there is just a positive charge here, right at the charge around it, it has very high potential. And as you go farther out, the potential decreases. Now I can take any point along this line here and measure the difference, or measure the potential difference between that point and the positive charge. Okay, I think we are ready to look into our lab simulations. The online simulations for charges, fields, um, basically introduction to static electricity. The course is electricity, magnetism, and light. Unit 1, you can complete your TA information here. Write due date based on when the TA sets it. Write your name and student ID. This is very important. Um, and before starting the lab, please read through the theory section um, provided in the lab manual. Um, Again, if anything you feel is incomplete or if you need more clarification, you can always refer back to the book chapters. Okay, once you complete the theory, uh, work on your pre-lab, and we expect you to complete the pre-lab before you come to the lab. You join the lab sessions. This gives you, general idea on what you know you're expecting in the lecture or in the lab. Um, and please type all your answers in blues so that it's easier to differentiate and easy to see your answers right away. And basically you'll type your answer here and save it as PDF and submit it back in the canvas. These are all the procedures for the lab. They're not separate, so the procedure and the lab activities go step by step. Here either gives the link to the lab, or these hyperlink, or the HTML, HTTPS separate link within here and ask you to click there. It will take you to the simulation, virtual simulation page like this one. So first lab today, is the balloon and static electricity. Okay, the question is you'll have to open this, explore to develop your own ideas about electrical charges from based on what you have learned from class or from the theory lecture today. You'll have to explain the different activities that we'll perform today. And they are here I made a note, but in your manual it should just be dotted line. It can be anything, so I'm just giving you three examples: one balloon, two balloon versus the wall remote. you know what what we are expecting from you is open this site and you can drag this balloon around. Okay, you can reset the balloon here. You can have so no charges, so charge difference, so no charge versus show all the charge. Initially these plus or minus together means the sweater is at neutral phase, because all the atoms are neutral, and the balloon has neutral atoms and the wall itself has the neutral atom. What I can do, I can move the balloon around and I can take this balloon and rub on top of the sweater. And you see, by rubbing the balloon on the sweater, the balloon has uh, attracted or grabbed all the electrons from the sweater, and it's there the electrons are lying on the surface of the balloon. I'm holding the balloon here in this pattern, in that region around here, and as you can see now, the sweater has net positive charge, the balloon has net negative charge. The positive and the negative, that's a attractive force. The sweater attracts the balloon, and if I release my mouse at that point and maybe not touching the wall or a little farther from the wall, you know, there's stronger attractive force between sweater and balloon, pulls them together. And if you look at it on the other side, since the balloon has the net negative charge and wall is currently neutral, but as I bring the negative charges here, it's going to repel the negative charges from the atoms of the wall to the right, and you see the electrons are pushed away from the wall. So you will have to explain why this is happening, um, in in these sections here, 1, 2, and 3. You can reset the balloon, meaning you're resetting all the charges, and you can have another balloon, two balloons here. Now rub some balloon with some charge and the other one, and now you see two balloons are charged with net negative charge. One balloon is going to repel the other one. If even you try to put it over here, now it's the positive, it's repelling all the positive negative charges to the right, and the positive and negative are attracting, and so on. So basically you'll have to explain these physical phenomena of these static charges, as you see it here. And so for every explanation from now on for all the online labs, please take a screenshot of these, like these for two balloon, what's happening, and for single balloon, versus if you have, let's say, two balloon and you remove the wall and you bring these two balloons together, the negative will repel and the balloon moves as far away from the negative charge as possible. Here the one conceptual question would be, when I leave this yellow balloon here, how far would it go, right? Uh, well, given that there is no string attached to the balloon, or when the string is there. So explain all these three or four phenomena, however many phenomena you see, but at least three. Here, John Travolta's uh, it asks you to explain uh, what happens, when you rub his feet against the carpet. It's, and you see the foot here is grabbing all the electrons from the carpet while rubbing it against the floor. And here other you can move his hand from
Ouch.
towards the doorknob and away from the doorknob. Okay, you can do two things, and you can explain so many physical phenomena based on two things. First, let me put the hands farthest out here, and let me rub the feet here. So here I can rub his feet as much as I want, and it's collecting all the charges possible. So his body is full of the negative charges, but they have nowhere to go. We're assuming the doorknob is electrically grounded, so the charge can pass through the knob to the ground. And so if I bring his hand closer, so
Ouch.
so you see, even at this high distance here, because there is so much potential difference between
Ouch.
due to all the charges stored here versus the ground, the knob, the charge, there's electrical breakdown happening, and this electron, jumps up through the air. Usually, air is an insulator; it's a bad conductor, right? It should not conduct electricity, but when there is enough charge, uh, the that's when the electrical breakdown happens. The field between the hand and the knob is so strong, there is this ionization process happening within the air molecules, and that allows the passage of the electrons from hand to the knob. Okay, and when the hand is very close to the knob, and even with a small amount of charge, you see it passes through it. But if you increase the distance, you would need more charge
Ouch.
for it to discharge to the knob. Okay, and that's what you're explaining here. So capture images for different positions of the image, different position of the hand, and these testing your understanding. These are uh, multiple choice questions. You have two options, A and B, but you'll have to go back to your previous balloon experiment and do the experiment, and also include the image to support your answer for either choice A or choice B. Same thing here, question 2, question 3, and question 4, back to Travolta's. Uh, this is again the two balloon experiment. This is also an interesting one, the electric field hockey. And you you can watch a short video here, or you can do your own experiment. This helps to understand the attractive and repulsive force, also the electric field, both, right? So the red line here represents the direction of the force. This is a positive charge. That's also a positive charge. Here, I haven't, given the charge its value. Let's say it's just a neutral symbol, and if I if I want to add a positive charge to it, I'll have to start it. So that means right now these are like neutral balls, and this gives me the direction of the force. So force is a vector quantity. It has magnitude and direction. Closer the two charges are, bigger the magnitude. The length of the arrow represents the magnitude of the force, and the direction, it's horizontal, and as I bring this charge downward, so the direction is about 45 degrees, 90 degrees, 180 degrees, 270, and 360. So the direction of the force is changing as I change the position of the positive charge. And now if I place the charge here and start it, now this is going to exert force on the other charge, and the motion of the charge, or the acceleration of the charge, is along the direction of the force, and that charge continues to move along that line. And if there is no resistance, then what happens? This charge will simply travel to infinity. And this is a hockey game, so I would like to point my acceleration of force direction towards the goalpost, and once I start it, you know this the repulsive force is going to push the hockey puck towards the goalpost. I can do it different way. How? I can set a negative charge here. I don't want that positive charge, leave it out here. See, the negative and the positive also have the attractive force. Oh, what am I saying? Oh yes. So if I start it, so here the force was, this is interesting. Um, the There's a attractive force between these two all the time, so it attracts, and with that momentum it gets to the other side. However, there is again that attractive force. So if there is no resistance to stop these two things, these will go on infinitely oscillating around it. I can do it maybe here. Why is it doing that? What's happening? Start. I can leave it here, and you see first the the acceleration is small because the force is small when it's farther out, and it starts to accelerate as it goes, as it reaches the negative charge, because the force is proportional to the distance squared, and so on. Here you can do so many interesting things. I can add, so if you want to increase the force, what I can do, I can take two positive charges, okay, and here, if I place two positive charges in the same line and have these, you know, aligned, the direction of the acceleration is aligned due to both charges, you see it's much faster because the force is equal to mass times acceleration, and the force exerted on the positive charge is due to the two positive charges, the red ones over here. And force is proportional to the product of the charges, so meaning more charge means more force. And so now I have three charges, it should be even faster. Okay, and interesting thing, do you have to press along the horizontal line, or do you have to put these charges in along the horizontal line all the time? I don't know. Let's see. Uh, I don't need that. So which way do you think the black hockey puck will move? I'm gonna start it, meaning give charge to these two two dots, two positive circles. So that's your vector concept. Okay, what I what I mean is electric force is a vector quantity. Okay, so there is electric force on the puck due to the bottom charge. The force is directed upward, and the electric force from the top red charge on the hockey puck is directed downward. So there are two forces, F1 and F2. What's the net electric force? It's the vectorial sum of the two forces, meaning this vector has x component to the right, y component up, This one has x component to the right and y component down. They both have same magnitude. So the y component is upward and here the y component is downward, so they cancel. So what is the net force? It's the force along the x-axis. So you're adding the x component of this vector plus the x component of this vector, which is both to the right. Hence, the direction of the force on the hockey puck will be along the horizontal to the right. What's the magnitude? That's your f cosine theta, f1 cosine theta plus f2 cosine theta. Hence, the resultant force is directed along the horizontal to the right. I know that hockey puck will travel to along the straight line horizontal and make it to the goal post. Okay, so with all that explanation, you should be able to answer most of these questions. And now, here in the fourth part, open the charge and field simulation, and you'll need to find what the potential uh, the potential difference due to the charges, and based on your potential difference calculate the electric field and plot that electric field here. So to find the electric potential, here you can set, choose what to include. I'm just there should be all clear instruction here, to what charge to place where. I am gonna use the grid line here, and so this NC means nanocoulomb. Okay, 1 nanocoulomb, the magnitude of this positive charge here. I'm going to take 1 nanocoulomb charge here and place it at the center or anywhere in this axis. And these bigger axis here, I believe this one small division is zero point 0.1. So notice the scale is 0.5 meters for one big box. So one small division is zero point 0.1 meters. Okay, and so these here you can not show the electric field direction. I would like to show the electric field direction. So from this charge, electric fields are directed along this arrow, and this field gets weaker and weaker as you go farther out, right? Closer to the charge, a stronger electric field. Um, and what else I can do? I can measure potential. So this one here, this device helps me measure the potential, uh, along any point. So I'm gonna put it at the center of that crosshair point, and you know, I get about, wow, that's a lot of charge. So you get about 1,000, little over 1,000. That's all right. So about 1,300 volts there at the center. Uh, the potential, okay, electric potential due to that positive charge, and that's what I'm going to write over here, potential at the center of the charge. And the electric potential goes by 1 over r, meaning the potential decreases as you go farther out from this positive charge. So what I'm doing with this device is I'm measuring the potential difference between 2 points. What 2 points? The center point, or call that V1, and that's my, X1 and my X2. So as I go to the right, the potential decreases. So basically now I'm measuring the potential at zero point 0.1 meters away. So I had 1,000 volts at the center, and I go 0.1 meter to the right. So the potential difference between these 2 points is 93 volts. And here, so the distance, this is at the center, call that V1, And as I go to the right, so increase that distance up to 2.5 meters, and each small division is zero point 0.1 meters. So you go to the right and you measure that potential up to 2.5 meter. That gives you V2. So the potential difference is delta V, which is V2 minus the potential at the center, which was about 1300. Okay, if you get 1200, that's fine, but it's more than 1000. And so you get the difference here, and that difference will be negative because you're measuring between two different points, and the potential difference can be positive and negative. Okay, it just which reference depends on the reference point you take. Here we are measuring between the farther distance, which has a smaller potential, than the center, which has the higher potential. So you'll get the negative, which is okay, but that gives you delta V, and by definition your uh, potential is electric field times the, the distance, and we can solve for electric field, which is delta V from here divided by D. Okay, here for electric field, I'm leaving negative sign there so that if you have negative potential, then those negative sign cancels and you get positive electric field. So now you have varying electric field, varying potential difference for different values of distance for one nanocoulomb charge. And so what I would like to do is now insert a graph here, meaning use Excel file, and plot the distance, electric field versus distance. Okay, if you go back to your formula here, your electric field, is it here? Uh, it was in the earlier, oh, here. Your electric field is 1 over r squared. Okay, so that means your electric field as you go farther out decrease by 1 over r squared. R is the distance here. So you should have 1 over r squared graph decreasing when you plot electric field versus D. And copy that whole graph from the Excel file and place it here. So here we're trying to see the relationship between charge and potential. This one is the sensor, guys. It's also for there are some conceptual questions. It will help you explain the direction of the electric field. Uh, so this is the positive charge Q, um, right? And this sensor shows me the magnitude of the electric field. As I'm closer to the charge, that magnitude is maximum or highest. And as I go farther out, you see the magnitude of the electric field decreases farther out, and it goes to zero at the infinity, of course. Uh, can I have a negative charge here? Let me put a negative charge here, and now you see the electric field lines go from starts at positive charge and ends at the negative charge. Um, and these are color coded, very nice. And if I put my sensor around, as you see, basically it follows even if I don't show the electric field here, and I can check my electric field direction around these two charges. And at the horizontal axis, I know the direction of electric field should start at positive and end at negative, so it will be horizontal to the right, and here it should be directed that way. That's my sensor, uh, and there is one charge. I can bring my voltmeter and measure the voltage there for different number of charges. I'll be measuring the voltage difference, which is delta V, get from V2 minus V1. So this is my first charge. Measure the potential here and measure the potential 1 meter away. What is the potential difference, right? add another charge here, and now you have different electric potential. What is the potential difference for Q equals to 2? For Q equals to 2, or charge equals to 2, for charge equals to 3, 4, 5, get potential difference for all 5 different charges. Then calculate your electric field, basically divide delta V by distance, which is 1 meter. Then plot charge versus electric field. Note, stack charges on top of each other after aligning as best as possible. And so you get more accurate data if you stack one charge on top of each other. Right? If you place one charge little to the left or to the right, remember it's a vectorial sum. So the magnitude of the total charge can be different, slightly different if they are slightly off in the placement. Then plot the electric field as a function of charge number. So charge number versus electric field. You plot it, and you'll get a equation. You'll get a you fit that line. Fit that data point, and you'll get a straight line in this case, of course, with some slope. It will tell you, the graph will tell you if electric field is decreasing or increasing with the additional number of charges. You go back to your equation and see how electric field is related to the magnitude of the charge. And here, this is more conceptual question I explained in the theory before. The how are the gravitational field and the electric field, electric field similar. Compare the two equations, that E equals to kq over r squared versus gravitational force is g m1 m2 divided by r squared. Talk about the direction of these fields and its relationship to the distance between the two charges versus between the two masses, and give 2 or 3 similarities and differences here in the fifth part.